Alrighty, welcome back to our regular calculus class here. We are now finally rolling into, I think it's 4-1. I sure hope so. That's what I'm prepared for today. So here's hoping. So we don't have any homework to go over, which is nice. So we can just jump straight into the material. And I think you're going to enjoy this quite a bit. 4-1 is all about what's called the antiderivative. So what is an antiderivative? Well, an antiderivative is what you get if you differentiate backwards. So let's say that I have an equation f of x equals 2x. So the antiderivative, and I'm going to try not to write this out too many times because it is a long word. The antiderivative is what would I differentiate to give me 2x? So what would I differentiate, which I'm going to abbreviate, to get 2x? Alrighty? So what would I have to differentiate in order to get 2x? It's very strange to think backwards like that, but that's what we're going to be doing for at least until we develop some good rules for that. So that answer would be, drum roll, x squared. If I differentiate x squared, I get 2x, right? Well, that's not the whole story, but we'll run with it for just a second, then we'll say what it's missing. So um, what you can kind of think of this is the way that your book lays it out is it lays some very formal language with this, which is not a bad thing, not a bad thing at all, but it can be confusing. So I'm going to try to translate kind of what your book says. So the definition of the antiderivative from the book is a function capital F, note the capital, is an antiderivative of lowercase f on an interval I when f prime capital F prime of x equals little f of x for all x and I. So that is, like I said, a lot to take in. What that means is the antiderivative that I find, let's say capital F, like that, that antiderivative, when I differentiate it, gives me back my original function. So you can imagine if I go this way and take the derivative, which would be, if I took the derivative of this, it's kind of an f prime, right? Big F prime. So the way that it's set up for the definition is a function capital F is an antiderivative when the derivative of capital F gives me back my original. And that's kind of what we were thinking from the get-go from what an antiderivative could be. All right, so that is in a nutshell what an antiderivative is. It is an inverse derivative. It's working backwards now. And you always can say to yourself, what would I differentiate to get my f? That's the antiderivative. Okay? But that's not the whole story. It would be lovely if that were, but it's not. What about that? If I differentiate this, do I get 2x? Well, derivative of x squared is 2x. The derivative of 1 is 0. So, yeah, I would get 2x again. What about maybe x squared plus 317? Yep, that still works. If I differentiate this, I get back 2x, but these are not the same. X squared is not the same as x squared plus 1 is not the same as x squared plus 317. So what's going on there? Well, we have to be kind of careful when we're talking about antiderivatives. Since the process of differentiating will eliminate any constants, when we go backwards, we need to be careful and say that each of these is an antiderivative. X squared is an antiderivative, x squared plus 1 is an antiderivative, and x squared plus 317 is an antiderivative. It is not the antiderivative, okay? It is one of many. So let me take this and show exactly what's going on. If it's okay with you, for just this example, if I actually had good sense, I'd be over here and draw that. Let's say that f of x is 2. What is big F of x going to equal? Well, 2x 2x plus 1, and then maybe even 2x. I'm not doing 317. 2x plus 3. We'll leave it like that. All right? All these are completely legitimate antiderivatives. What do they look like? Well, if I go over to Desmos, which I sure hope I can do here, let's see, open it up there. Cool. All right. So what is the difference between 2x, I'll be good, y equals 2x, and then y equals 2x plus 1, and y equals 2x plus 3. What's different about all those? Well, they're all different. They're parallel, that's for sure. One of the things that I hope is just instantly jumping out is they all have the same slope, right? So when you think about it, these antiderivatives are the backwards inverse of a function that when I differentiate the antiderivative, I get the function back. So in a way, this is a weird way to think of it, when I think about going backwards to the antiderivative, all that it can change and still be legal for when I differentiate the antiderivative to go back is the, how to say this, the slopes are okay. They are all going to be exactly the same, but the y is what can change. I can have any y I want. I'm going to go back. We've all seen that these are all parallel. They're all stacked on top of each other. Let me go back to the drawing board so I can show you what I'm talking about. Let's see. Turn this off. Okay. I have f of x, little f of x is 2. The antiderivatives, some of them are 2x, 2x plus 1, 2x plus 3. Okay? Now, I went backwards to get these antiderivatives, right? But you could also think about going from the antiderivative to the function, you take the derivative, right? That's what we said right here. If I want to go from the antiderivative back to the function, I just take the derivative. So in a weird way, when I go this way, I'm taking the derivative. when I'm trying to get back to the original f of x. I get that by doing the dx of f of x. Okay? So what's preserved? The slope in this case is preserved, but the y-intercepts are not. I can put any y-intercept I want, and I'll still have the same slope. 2x minus 512. That's just a different y-intercept, but the slope is exactly the same. So we had to be careful when we talk about antiderivatives, because all antiderivatives can have different y-intercepts. They can be different, have different offsets. The rates of change are going to be the same, but the constants, where it's located in the y-axis, can be completely different. Alrighty? I hope that makes sense. That's a very tricky concept first time you see it. Alright. So, with that said, let's go down to the next one. There's a theorem. We have a theorem here. This is I will honestly say, one of the most confusing of the theorems the first time you see it. I didn't like it at all first time I saw it. So what does it say? It says that if capital F is an antiderivative of little f on the interval I, then big G is an antiderivative of f, little f, on the interval I, if and only if G is of the form capital F plus C. Okay, that's a lot, where C is some constant. Let me go ahead and clear this, and then I will work through that. It's not bad at all once you kind of work through it. It's just very poorly worded, in my opinion. So basically it says I have some f of x, maybe 2x, and then I have some capital F. Okay. It says that G is an antiderivative of f if it is the same as f of x plus some constant. In other words, x squared plus any constant is also an antiderivative. Like I say, it's not as bad once you break it down, but boy, do I not like the way this book words that at all. So this is basically saying what we've already said, is that you can have as many antiderivatives as you want, as long as they differ only by a constant. They're all good. Okay? So, I know that was a lot to take in. Let's go on to the next one, and we'll start working some examples here in just a sec. Alrighty, so here we go. When we're talking about all this stuff, it's very important to have the same kind of language with this, because things get really confusing really fast if we can't say the same words and mean the same thing. So this C here has a name. It is the constant of integration. So now, hopefully at this point, like, alarm bells went ding, 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 ding. What is this integration of which you speak? We're about to get there. It's coming. So it is the constant of integration. It is the constant that you can add to any antiderivative, and it's still an antiderivative. It is still an appropriate antiderivative. All of them are a big family that are just, they vary by the y value offset. That's all it is. Alrighty? So this g of x, when I say g of x is equal to capital F of x plus c, when I say that, it is locking down that this g can have any constant of integration, and it kind of pulls it into the family. So g of x includes f of x plus 2, f of x minus 17, f of x plus pi. It doesn't matter. As long as it's a constant, g of x has it. It is part of a family of solutions. So this has kind of a term, and I'm kind of glad that they used g right here, even though it just happens to come after f is 1. I guess they said it, but this is the general antiderivative. I'm smiling because we're not going to say the word antiderivative for a whole lot longer. We got about 2 sections, then we're done with it. So the general antiderivative is one that has the antiderivative plus c, because that c can be any value that's a constant, and so it kind of pulls everything together into one big family. Alrighty? So let's do a little bit of practice with some of this notation. First, let's start off with f of x is little f of x. Let me block this. Little f of x, I'm going to change colors too, just because I want to. Little f of x is equal to 2x. Alrighty? So now that little f of x is equal to 2x, what does capital F of x equal to? Well, capital F of x is equal to, really, you can kind of think of it as, it could be anything as long as it has a c attached to it. So, or it depends on how we want to work with it. Let me actually foreshadow ahead. Oh, I didn't do it. I forgot to do that. Oh no, sad day. Oh well. We're just going to have to muddle through as best we can. No, I'm actually going to crack the book open right here so that I can make sure that I do it exactly like your book says, so that we can all be on the same page. So your book says at this point, I believe, that's it, really? Oh, I thought it would be more interested in that. No, it's not. Okay, cool. That works. Not interested at all, so we'll just knock it out. The way that we kind of have it written here, this f of x can be any, you know what? I'm going to say it like that. F of x, we're just going to do the antiderivative without the c. That's the capital F. That's a specific value. It could also, if I wanted to be, plus 7. But the g of x is where you add the c. This is the real answer right here, because this is a specific y value, a specific offset, but I don't know that for sure yet. It could be anything. All I know is that I started with 2x for my little f function, and then I went backwards differentiating, and what do I differentiate to get 2x? X squared plus some constant if I want to include the whole family. Alrighty? So that's kind of the way that we're going to talk about it from here on, is that the general antiderivative is really what we're looking for, the plus c. When we go backwards, that plus c incorporates every possibility that you can think of that's a constant. But here is a very strange question. What is g prime of x, big G prime of x? What's the derivative of big G? Big G, what's his derivative? Right, the derivative of this is 2x. The c is a constant, it goes away. So really, the derivative of the general antiderivative is still the same thing. It's still the function that you started with, which should be. If it's not, we've done something terribly wrong. So that is comforting in a way. Alrighty, so now let's go down to the next one. Alright, so we talked about that, but let's do some definitions here. Alright, this right here, we said it was a general antiderivative. It is, and it is the correct antiderivative. But sometimes you're going to see in a slightly different form, in a slightly different context. So you could say that, this is going to sound weird, this is a general solution to this up here. Would you agree? It is the general antiderivative of the original f of x, right? It's a general solution for this little f, okay? But little f can be written as g prime. We just discovered that when we did the g to the g prime. So really, a way to look at it is g prime, the solution to that is g. When I talk about the general solution of a g prime, I'm talking about finding the antiderivative. But that is really, really, really confusing. I'm throwing terms all over the place, so let's nail it down. I'm going to go to a different color. Let's see. No, that won't work. Let me go for, I think I just erased my pen. No, I'm good. Oh, I don't like that color. Orange. Orange. What on earth am I talking about? Well, one of the things that we're going to be doing with the antiderivative, besides it has many, many, many uses, but one of the things that we can see immediately without doing some more stuff that's coming is that what if I have a prime, but I want to find the original? So, in other words, what if I have dy dx equals 2x? Okay? This is the derivative of y with respect to x, and it equals 2x. But I want to know what y equals. Well, y is just the antiderivative of this. So you could say that, and we already know what that is, the antiderivative of dy dx gives us y, the antiderivative of 2x gives us x squared plus c. Okay? This right here is the general solution. Now, that may look, why on earth would we ever do that? That doesn't make any sense. Well, the reason that we'd want to do that is because, let's say that we're doing something in the lab. Maybe we're monitoring a chemical reaction. That chemical reaction, we can measure it's doing something at a certain rate. But what I want to know is, what is the amount of x at any point in time, not the rate at which it's evolving. I want the actual amount. So what we want to do in that case is to go from the rate of change that things are evolving under back to the original equation that describes the amount of something that we have at any given point in time. That is an extremely common thing that you would want to do. And I don't want to spoil it, but you can imagine in physics, you could measure the velocity of something with a radar gun, for example. By doing the antiderivative, you can back out the original position that was at every single instant in time, assuming constant acceleration. So I know it's a lot to throw at you, but just to walk through it, it's not bad at all. You start out with a little f of x. You find the antiderivative of that. You add the plus c to it to get the general antiderivative, which is also sometimes called the general solution, but usually the general solution is in reference to solving this type of thing where we have a rate of change and we want to know what the actual amount was, the inverse of that. So this is called a differential equation. So this dy dx equals 2x. That is a differential equation. Why is it called a differential equation? Because it has a derivative in it. It is an equation that has a derivative, and it's a derivative of y. The derivative of y with respect to x equals 2x. That's a differential equation. Okay? And so when we go backwards and find the general solution, instead of dy dx, we have just y. And then we have the x squared plus c for the general solution. I think I beat that horse into the ground pretty thoroughly, so I think we're good to move on. Alrighty. So let me go to the next slide. Oh, here we are. Y'all are so fortunate. We're at a very fun spot. Okay, so here we go. This constant of integration that I talked about, turns out that no one goes around saying antiderivative. It is a really precise term, although I guess inverse derivative would be better, but it works. It sounds a lot better. It tells you what it is, but it doesn't. It's a mouthful. Antiderivative, antiderivative, antiderivative. So we have another way to reference the antiderivative, and that way to reference it. Let me clear this and so I can write this down. The antiderivative is the same thing as what's called an indefinite integral. You just said we save syllables. Well, we will eventually get away with removing the indefinite part, and by context we'll know if it's an indefinite or a definite. So the antiderivative and the indefinite integral are exactly the same thing, but it comes with some new symbols to represent the antiderivative. Way, way, way better than saying, what is the antiderivative of y equals 2x with respect to the x? That is just a terrible amount to say. So what we've done instead is we've done some shorthand notation. So this right here is red. The integral, indefinite for now, the indefinite integral of 2x with respect to x. All of that is wrapped into this one little expression. So the second you see this little S symbol, I draw a horrible integration symbol. That's what I should be drawing. But that hurts. I can't. I don't even like looking at that. I don't know why, but I love looking at my little weird S's. So y'all are stuck with it. Some professors do really, really nice notation for integrals. Mine just looks like a sloppy S, but it sings to me. So you're stuck with it. So what does this mean? Well, this is saying find the antiderivative of 2x with respect to x. We're not going to have to worry about that for a while, but for right now, it's just saying that we want to find this antiderivative. And we know that the antiderivative for 2x is, what do I differentiate to get 2x? Well, I differentiate x squared. But I have to remember to add that c, that constant to it. This is the general antiderivative, which is what we're looking for when we do the indefinite integral. Okay? So this is right here the indefinite integral of 2x dx. That's what that is. It is the antiderivative, the inverse derivative, plus the constant that you have to tack on at the end. All right? Hopefully that's not too bad. I wish I could hear y'all like going, no, slow down. Or, yeah, it's not bad. I hope that's not too bad. But wait, there's more. This section is chock full of stuff. Like, it's just tons of stuff inside of it. But this stuff right here is it's kind of obvious when you really think about it. If the integral, if the integration, if you will, is the inverse a differentiation, then they should wipe each other out, right? Because that's what an inverse should do. If I have my little thing, if I take the natural log of e to the x squared, that's just x squared, right? Because they wipe each other out. So now, with the integration being the inverse of differentiation, they wipe each other out. So I can say the integral of a derivative, if I had good sense, let me erase that. Well, what is that going to be equal to? Well, it's going to be equal to the original function. The integral of the derivative of f of x is just f of x plus c. Whenever we go backwards, you have to add that plus c. But the converse is not true, because if I take the derivative of the integral f of x dx, that's just f of c, f of x. So why isn't that c there? Well, because I'm doing the derivative. When I go forward, I don't have to worry about a constant, because, well, any constants are gone at that point heading forward. But going backwards, when I do the antiderivative or the integral, I always have to make sure I have that constant down there. So there you go. Alrighty, so we're going to stop right here for this section, and then we will pick up with the remainder in just a second. So I will see you in just a sec.